Good morning to all. So today we will start with the our professional elective number 6, that is robotics and artificial intelligence. So first of all I would like to show you the syllabus. Okay, I will share my screen. So this is our syllabus. So the name is professional elective 6, robotics and AI. Okay. So you need to know the basics about machines, instrumentation and control system to understand this subject in a peaceful manner. So it has 3 credits. Okay, we have T1, T2. T1 might be start from the next week from 22 March onwards, and ESE is of total 60 marks. And so now these are the syllabus. Okay, the contents starting with the introduction, then elements of robots, then the kinematics of the robots, then the velocity and statistics of the manipulators, and then the motion planning and control, and lastly the artificial intelligence in robotics. These are the books. First one is the Robotics Fundamental Concepts and Analysis, okay, of Oxford University Press by Dr. Ashitawa Ghoshal. Okay, I'll show you the preface of this book. This is the book, okay, by Ashitawa Ghoshal, professor from IISc Bangalore. So he has written this book very nicely, and the syllabus has been structured. Most of the contents has been structured from this book. Okay, you can refer this book for your reference. So we will start the lecture. Okay, I will share the PPT. Okay, so you can see the slide. So introduction for this. So the origin of the word robot is in 1923. Okay, and it is basically a translation of a Czech play. Okay, with Czech Republic play called as RUR. Okay, which is also called as Rossum's Universal Robot, which is in 1921 by Karel Capek. Okay, so this appeared in an article by this author Capek in 1971. So the word robot is from the Czech word robota, meaning slave labor. Okay. So in the play, as it is shown that the robots are designed to replace the human and depicted as very efficient and lacking emotion. Okay. Even today, this description is very prevalent and relevant. In 1970, Asimov wrote or coined the word robotics in this book or article called as Roundabout, and he proposed 3 laws of robotics. Okay, so the laws of robotics are incarnated from that time. Okay, 1970, and in his portrayal of robotics, these are portrayed as harmless and in control of humans. This was a theory regarding the Asimov. Okay, so there is 3 laws of robotics, very well known. Okay, we all know that. So things like a robot cannot harm a human being also. Also, a robot must protect human being and so on. Okay, so these are the 3 laws. So he wanted to make robots much more human friendly. Now, the first industrial robot patent in 1954 by George. Okay, so this is a patent number. So the patent number you can search it in the net. That is 2988237, and it was called as the Universal Automation or Unimation. Okay, the first robot was developed by a company called Unimation Incorporation. Okay, and it was found by Engelberger and Devol, the same person, who the same person like DeVol who patented universal automation, and they called it Unimate. Okay, so this robot was used in General Motors plant. Okay, GM motor plant in Trenton, New Jersey. Okay, it was automobile plant. This robot was used for handling die cast material for spot welding. Okay, you can see here. There are many examples of robots, and there are many modern robots. Now I am showing you few of these pictures. So for example, this is very known Puma robot. Okay, Puma 650. This one. This Puma 560 robot appears in all textbooks of robotics because all the geometry and parameters of these are known, and we can do analysis and modeling of Puma robot very well. Okay, so this is used to teach robotics, kinematics, especially in a simple manner. Then you also have this very well known space shuttle arm. Okay, you can see here it's in the space and it is a space shuttle arm. This is very lightweight, and this is very flexible robot which was put on the space shuttle, and it was used to deploy the retrieve satellites. You also have a mobile robot which is on Mars, okay, which is roaming around the Mars. Then there are these well-known industrial robot companies. So there is Fanuc, one of them. Okay, it is a Japanese robotic company. This is a Fanuc Robotics Incorporation, and they make this huge line of robots. Many robots. They sell lots of robots around the world for the industry. We also have robots which are now used in surgery. You can see here the picture. I will show you a video. Okay, after this, 3 to 4 slides. So this is a well-known Da Vinci surgical robot. Okay, we have also robots as humanoids. Okay, so there is a robot which was developed by this Honda company called Asimo. Okay, this one Asimo. So this Asimo is a humanoid robot which is smaller than the human beings. Okay, and it has features like it can walk, it can climb the stairs, and so on. There are also robots which are now available as toys, which are used by children, like this one. This is popular kit for making robots. There are also, so you can build your own robot from this, and this company is called Lego Mindstorm. It is very well known. Okay, this is a Lego robot. If you have played while in the childhood with the Lego, you can understood this kind of things. So there are also very other famous robots. One of them is a Stewart platform. Now you can see here, this is a Stewart platform. Okay, this was originally developed for tire testing. Okay, testing of tire. However, nowadays the Stewart platform is most often used in the simulation of flights, different flights. So basically, there is a cabin in this robot in which there are video screens, okay, in the cabin, and there are on some joysticks and control, okay, for simulation. So as you move the joysticks, so there are the legs, okay, these are the legs, extendable legs. You can see there. This is the cabin. These are the extendable legs, and so as you move the joysticks, these are the legs which can be extended. Okay, so if you have 6 legs, you can count there are 6 of them. As you extend or retract these legs, this cabin can go up and down in XYZ directions. Okay, up and down in XYZ three directions, three dimensional. All the directions it can also do roll. Okay, it can also roll, it can pitch, it can yaw. So a person sitting there here can be trained to fly an aircraft by using all the video screens. That is the application, okay, for which steward platform is used. There are also nowadays new robots which are used for exploring the underwater like this. Okay, so this is the robotic fish. It looks like a natural fish, but it has arms and actuators in this construction. Okay, so it is developed under the guidance of various universities, ocean universities. Okay, research technologies. So for example, MIT have worked. MIT means Massachusetts Institute of Technology. Okay, in Massachusetts have worked a lot on this kind of robotic fishes. Okay, the ocean department of that institute. There is also toy dog developed by Sony. You can see here this was famous in the late 20s in Japan. Then there are these bipedal robots. Okay, you can see here you see bipedal walking robots. So they walk like a human beings. Okay, replica of that human being. They have been proposed to use in the space, but use in the space and on surface of the moons and on surface of the Mars also. Now I'll zoom this. Okay, the mouse cursor is not quite visible. For convenience, I will zoom this. Now here, hmm. And there, like we will go through this next one, that is flying robots. These are called as drones. Okay, nowadays you can see a lot of drones that are used. Okay, for video shooting, also for the weather forecasting. Okay, and for different spying purposes. Okay, these are called as drones. So you can have a robot with some actuators which are basically propeller, and several of them, and then you can go and fly and reach many places. Okay, by this uh, drones. Okay, these are the different parts of the drones. So these have the drones have become a very popular nowadays because you can control these drones for large number of applications. You can go over forest, you can go over the agricultural fields, you can also go to places which is not so easy for human being to go by this. And it can take pictures of that area, it can record the videos in high definition. Okay, even it can record videos in 4K with image stabilization. Okay, IES, we can call it as OES, optical image stabilization, etc. So now even there are many different kind of robots. There is no uniform or a single definition of robot. Okay, in spite of this, so the best possible definition of a robot is by Robotics Institute of America. Okay, it is a little bit historical. Nevertheless, it is worthwhile noting how it was defined in 1969. Okay, so robot is defined as by the institute, that is, it is a reprogrammable, multifunctional manipulator designed to move materials, parts, tools, or specialized devices through various programmed motions for the performance of a variety of tasks. Okay, so all these words are very important, which are reprogrammable, multifunctional, designed to move materials, parts, tools, and so on. So it is a little bit biased towards use of robots in industries. Nevertheless, it is a very useful definition to keep in mind. Currently, the term robots are used much more broadly, okay, in a broad manner. Some people call it intelligent agent. Some people can even say physical or virtual. Okay, it can be virtual robot as it is capable of doing tasks which are autonomous or with guidance. Okay, so for purpose of robot is an so for our purpose, a robot is an electromechanical machine with sensors and electronics devices, and it is guided by the computers. Okay, the key concept above in this definition, which is still valid, is that a robot is reprogrammable. Okay, and what do we mean by reprogrammable? So it does mean that a robot can do a variety of tasks. So it is much more programmable than a CNC machine tool. Okay, so in case of CNC machine tool, it can cut or mill or do various things, but the robots is much more flexible than CNC. It can do painting, it can do welding also, so a variety of tasks. It can do material handling and so on. Okay, and so this word reprogrammable is still a very valid and very important in case of robot. So now the advances in robotics has closely followed the explosive development of computers and electronics. Okay, so according to Wikipedia or Wikipedia article, the devil author used his patent on magnetic recordings devices, okay, for brains of his Unimate. So this was the first robot which was built in sold, okay, and in order to program them or reprogram them, he used this magnetic recording devices. The first computer, that was ENIAC, was developed by University of Pennsylvania in 1946, and the first transistor device was built by Shockley and Pearson in Bell Labs in 1940s. Okay, both of these are very important dates in the history of robotics. Okay, so without these computers and without the transistors, a lot of modern devices are not possible at all today. So not so easy to make also. Another key ingredient in the field of robotics is, or the history of robotics is, the concept of feedback control. Okay, so the first textbook or the reference book on feedback control is by Professor Norbert Wiener of MIT in 1948. So we will see that the feedback allows execution of a program which is a desired motion by a robot and a large number of devices. You can do program many other devices with the required accuracy. So I want a robot to do some task. Okay. Let us say I want to weld some different materials. But how do you make sure that is that it will weld the material accurately? So this whole notion of feedback is used to make sure that it performs the desired motion with reasonable accuracy. Okay. So initial usage of robot was primarily industrial primarily was in industrial applications such as part handling or material handling and welding and painting and in few handling of hazardous materials. Okay, now so the initial die cast piece, okay, which was handled in this General Motors plant was very okay high temperature. It was very hot. So it is a sort of not so easy for human beings to handle this object, which is coming out from a die cast material. For that purpose, robot was used. Most initial robots operated in this support teach playback mode and replaced repetitive and back-breaking tasks. Okay, so what is teach playback mode? Okay, you might be curious about this. So basically, you teach the robot to do a set of tasks, different tasks. You record the motion of the joints, and then you record the motion of various parts of the robot. and then you take it to the factory, and then you can take it back. Okay, so it will repeat what you did earlier, and or what you have trained or you have taught earlier. And the advantage of this teach playback mode is that it can replace all these repetitive and back-breaking tasks. So if you want to do straight line welding, okay, which is very useful in some applications, a spot welding thousands of times in a day, I do not want human being or any other one to do this repetitive task. Okay, so a robot in this case is much more suit suited better for doing these tasks. Similarly, if you want to lift large weights, okay, which are in tons, okay, which is much more easier for the robot to do than the human being. Okay, and from the earlier time, we are using robots to for weightlifting purposes rather than using it for humans. So growth and usage of robots have slowed significantly in the late 90s, late 80s, and early 1990s. Sorry for the disturbance. We'll start again. Okay, we have seen this teaching playback mode. Okay, so now the growth and usage of robot slowly, significantly. Okay, it has been slowed significantly in the late 1980s and early 1990s. Okay, so these robots, which are basically in teach and playback mode, after a while, industry saw that they were not that useful, and it turned out that it is due to the lack of intelligence and ability to adapt the changing environments. So robots before this 1980s were essentially blind, deaf, and dumb. Okay, so you can teach a robot to do welding, but if the two parts are not there, it will weld in air, and it was very wasteful. So in the last 25 years or so, sophisticated sensors and programming allowed robots to act much more intelligently, intelligently, and then also autonomously, and react to the changes in the environment much faster than the earlier. So again, robotics is very hot topic. There are lots of robots which have been developed, and importantly, there are more intelligent. Okay, they are more autonomous, and also they can react to changes in the environment. So we have self-driving cars, for example. In a sense of in a sense, that is a robot. It can react to a passenger or a person coming in front of the car, or some other vehicle coming in front of the car. So it can stop, it can react. Okay, so it can react. So again, this robotics field is catching on. Present day robotics are used in cluttered workspaces, in homes and factories also. So once very well known robot nowadays is a vacuum robot. Okay, so it can go around vacuuming your room or your house, and it will work in this cluttered environment of your house because it has table, okay, chairs, various things. Okay, so it can learn where these obstacles are, and it will learn how to avoid them. It can also safely react with our safely interact with humans, and they can be in close proximity. So basically, a robot can make sure that you do not hit the human. So there are robots called as cobots, cobots. Okay, cobots, which basically a human being and a robot will work together for certain task. The human being will do task which it is better at doing, and the robot will do some task which it is better at doing. Okay, so even now human beings can do very precise tasks, whereas robot precision level is are not that high. It can operate autonomously in hazardous environment. That is that advantage of robot. So for example, this Mars rover. So you have seen the Mars rover is roaming around in the Mars, taking pictures, okay, taking soil samples, analyzing various things, and it is also being used in entertainment and in improving quality of life. Okay, so these are some modern present day usage of robots. So let us look at few robotic applications. The first was the example of Fanuc ArcMate, okay, arc welding robot. So we will see a video after some slides. Okay, we can also have robots which are in hazardous environment. For example, the 3 Mile Island and the Chernobyl accident, okay, that has been done earlier. So that robots were used to clean up these nuclear power plants because the environment is so hazardous that any of human being cannot go there. Recently in Japan, there are robots called as packbots, which are used to measure radiation and taking the pictures inside the plant which was exploded. Okay, so we also have robots which are used in deep sea, very deep sea. For example, the Titanic ship, it was photographed by this submersible. Okay, the robots Alvin submersible known as Alvin, and underwater robots Argo and Jason Jr. Okay, it was discovered in 1986. We also have this space shuttle remote manipulator system. Okay, so basically it is happening in space, and this was used to deploy and retrieve satellites and other equipments. We also have electronic assembly and pharmaceutical manufacturing in clean rooms. Okay, in these situations, the human presence introduces dirt and its hazards of the product. Okay, so in the first three, it was hazardous for human being to be in that environment. If you want to go in a very clean room, it is best to send a robot because the robots will not be breathing and sending out particles. Okay, so you can also have very well known autonomous mobile robots and vehicles. Okay, so there is this Mars exploration rover mission. Okay, MERM, and more very importantly, there were this DARPA Grand Challenge, which helped in developing autonomous vehicles. So this DARPA, the US Defense Agency, said that if we should be able to travel so many kilometers in desert or in some other place autonomously without intervention by human beings. So you could have cameras, you will have lot of sensors which will make sure that you traveled in this terrain autonomously. Okay, and many of these technologies which were developing during this DARPA Grand Challenge are now finding it in the self-driving cars, which are becoming more and more popular nowadays. There is also robotic surgery using a Da Vinci robot that we have seen earlier in the slides. So next in the next slides, I will show you the video of this IIT professor. Okay, so he has explained the robots. Okay, they have in that video they have shown the video from internet, and they have given a basic little information regarding the application of robots. So one of the advantage of this Da Vinci robot is that it can be very accurate and it can be remotely located. So I could be doing surgery sitting in one places, but that patient is far away because I can send the signals using these computer networks, and then the robot will there do the surgery. Okay, this much this it can be used. So we can do remote surgery as we do remote desktoping very accurately. There are many other advantages. For example, a robot can move tremors. It can scale up or down the motions of the surgeon's hand. Okay, you can see very clearly the area where you are doing surgery and so on. There are also these micro and nano robots which have been developed at various universities and research laboratories. Okay, so if we would like to send a very small robot in your body to go and, let us say, remove some samples for later on biopsy or some other reason, or we want to take some measurements, so this should be very small robots. So these are micro and nano robots. For example, angioplasty and angiography. There are then there are these miscellaneous robots which are called as miscellaneous. Okay, but very interesting. So for example, there is a Robocop soccer tournament. So basically, you have to build the robots which can play soccer and following the rules of the soccer. There is also a robotic fish, that is a robot which has made by NASA. It is a humanoid robot which will go into the space for exploration of space. And then there are Japanese humanoid robots which have been developed which can even show facial expressions and emotions. So in the later next we will clear the video which will give you the information regarding the applications and the visual uh, display of the robots. Okay, in the terms of video. Okay, now I will play the video. Okay, we will start the video from here. Okay, I'm playing this. Okay, I can also play the video and explain you, but the language and the depth that the IIT professor has is much more better than me. Okay, that is the reason why I'm playing this video. So you do watch this video, and then we will start with the types of robots.
In the next few slides, I will show you some of the common applications of robots. Okay, so some of these slides are from the internet. So I will show you a robotic welding system, a robotics material handling system, a robot which is used in a clean room environment, and then two sort of newer applications, one that of robotic surgery and one a robot which can show facial expressions and are being planned for use in service sector. Okay, so let's start. So in this first slide, I'm going to show you a robotic welding system. This is from the internet. Okay, so what you can see is a robot which is manufactured by Fanuc. It is very well known. It can do arc welding. Okay, so the joints of this robot are controlled for welding tasks. Okay, and clearly the robot can be reprogrammed for different welding tasks. So this welding is very common in automobile industry where you want to weld certain automobile components. Okay, so as you can see here, the robot is moving the welding torch along a pre-programmed path. Secondly, it will also control a wire feeder which will push in the wire which is used in welding. It also controls the safety screen and other safety systems. So initially you could see that there was a black curtain which went in front, and at the end of the welding you will see that the black curtain is going back. So all these things are controlled by the same controller, so they are synchronized. One of the advantage of robotic welding is it has very high repeatability. it gives better accuracy, and it can give faster production. Okay. The next video is on robotic material handling. This is a robot which is made by Adept. It's a SCARA robot. Okay, it comes with the vision system, and as you can see, it can move very fast and pick some object from one place and put it in another place. Okay, it can perform these placement, picking and placing tasks very accurately. It can be reprogrammed for different materials and different kind of handling. It's a SCARA robot. So basically it has 4 degrees of freedom. So the end effector can move in X, Y plane. It can also go up and down. It has a Z motion, and it can also orient the tool or orient the part which it is handling about the Z axis. Okay. So this is a very well-known robot. It has been there for a long time. It can move very fast and very accurately. Typical speeds of this robot could be more than 1 meter per second. The next video which I am going to show you is a robot in a clean room. Okay, clean rooms are basically in electronic and semiconductor assembly places. So in such situations, actually the product is hazardous, okay, if a human being is there. Okay, the environment, if a human being is there in the environment, it is hazardous for the product. So human beings will generate dust, breathe, vapor, and that way if it falls on this PCBs and chips and wafers, it can spoil them. So in semiconductor assembly, robots are used extensively in clean rooms. The next video is also from internet, and this is a very well-known product. This is called as a Da Vinci surgical robot. Okay, so this is becoming very popular. The reasons being that it is very accurate. Okay, so as surgeon operating this robot, okay, can do it remotely. Okay, it can remove the hand tremors. Okay, so as you can see, the surgeon is seeing through some video screen, and the robot is far away, and the robot contains all these surgical tools. It can have several arms also. Okay, so going back, you can see the surgery area in a very magnified view. The computer system can also scale the hand motion. It can make it very fine motion, or it can move very quickly. So you can do, for example, move the joystick which the surgeon is manipulating large distance, but the actual tool will move much finer. Okay, so you can do surgery at very fine scales. So as you can see, there are these 2 joysticks. So basically you can move the end effector, in this case these tools, by moving those joysticks. So this is a surgery of something, I don't know. Okay, but as you can see, you can do suturing, you can do cutting, you can do various operations remotely by the surgeon. Okay.
Are enabled by the computer processors of the system.
So this is a very popular and very expensive robot also. Okay, so there are a few of them in India. They cost several crores in capital cost. They also have a lot of consumables. So each time you use this robot, some of the things have to be thrown away. So what is being shown here is the end effector of this robot. So you can move in various directions. You can also grasp things like threads and cut things like skin and so on. Okay, so some of these things need to be thrown away after a few number of surgeries. So there is a lot of consumable, and it is known that it can cost several lakhs to do some surgery.
Enables the surgeon to tailor the ratio of his hand movements to a corresponding micro movement at the instrument tip. The system requires that every surgical maneuver is under the direct control of the surgeon. redundant safety
Okay,
chips
another big
affect
advantage of
autonomous
this Da
movement of the
Vinci
instruments
surgical
or the
robot is
robotic arms.
the surgeon could be
The
sitting
Da Vinci
someplace
S
and
surgical
the
system
robot could be
adds to
sitting
the
far
enabling
away, and then
characteristics of
the
the
surgeon
original
could
Da
do
Vinci
the
to
surgery
streamline
remotely.
surgery for the entire OR team. Da Vinci
And
S
it has been
provides
shown,
fast, foolproof setup,
demonstrated
including a motorized
long
patient
time
cart
back
for
that the
simplified
surgeon
docking,
was sitting
simple
in
click-lock
Europe
cannulas,
and the surgery was being
rapid
done in
instrument exchange,
America. Okay,
and an
transatlantic
intuitive
distance was
touchscreen
also shown.
interface.
Remoteness.
Intraoperative communication between the entire OR team.
And as I
is
said, you
enhanced
have a
with
very
the
good
audio-visual
viewing system.
components
You
of the
can
system.
see the things
internal
in a
view
very
of the operative
magnified
field
form,
is
and you
visible
can
on the
see
vision
very
card
clearly
or optional
where you are
patient
doing the
cart monitor.
surgery. So it
These
has
monitors
lots
can
of
also be
advantages.
toggled to display
Okay,
patient-critical
except for the
information
fact that it is
or a
extremely
tile
expensive,
display with multiple
and
windows.
hopefully the prices will come down in future,
Proctoring is
and this will
enhanced
become
with the
more
telestration
common and
capability.
popular.
Notations drawn on the patient cart monitor can be seen by the surgeon as an overlay.
Okay, so
on the
I think I'm
surgical
going to
view of
stop
the
here.
console. The two-channel
But
endoscopic cameras
let's
of Da
continue.
Vinci.
This is another video from internet. It is of a humanoid robot. This video is about 10 years old and it was created in Japan. So as you can see, it shows a humanoid robot which is capable of showing facial expressions. It can recognize voice commands. It can react to voice commands. Okay. So you can see how realistic this robot is. The motions of the face, the lips and the eyes and the neck, everything is becoming more and more realistic.
Hello, my name is Eiko. I was created by La Trump. I have the ability to have conversations.
And robots such as this are expected to be seen in banks, in various other places where you require information. So they are going to come in the service sector, okay, where the person asking can ask very different questions and the robot has to react to those questions. Okay, so it is showing a lot of autonomous behavior and intelligence.
These are some of the features I can do. However, a full demonstration of my ability will be performed during my public appearance. Hopefully, one day my creator will be able to make me walk and interact
So
with the
this video doesn't have voice, but as you can
What
see,
is
it can
your
move
name?
its lips.
My name is
It can,
Aiko.
as if it is talking.
Echo, how's the weather outside?
The current temperature is 17 degrees with clear sky and no precipitation. And
Let's fast forward. It can even recognize objects. It can even
Echo,
respond
tell me what you do pain.
to speech
understood.
and move
I
its
will let
arms.
you know.
Okay, so it can do various
I am
things,
starting to feel it.
almost like a humanoid.
Please let go
Okay,
of my arm. You
so
are
with this
hurting
we'll stop here. Now let's come back to ISC and what are some of the work which we have done in ISC. So I am going to first show you a hyper-redundant snake robot. Okay, so this is a multi-link snake robot, and as you will see shortly, it consists of 12 links. So there are 12 motors which can rotate these links, and there are also some wheels, okay, which are also rotated by motors. So the wheels have to drive this snake robot forward. So we compute the motion of the robot using this Tractrix algorithm, which I have discussed earlier, or we will discuss later. So it makes sure that the robot avoids all these obstacles. So in this case, this is moving on the floor, and these are some obstacles which have been put there. The path of the head and the location of the obstacles are known a priori. Okay. However, later on, if you have a sophisticated robot with enough computing and enough sensors, it can look ahead and see where this obstacle and then plan the path. In this video, the path is given. Okay. So basically what it is doing is the algorithm is showing you that it can compute the motion of the body of the robot such that it never hits any of these obstacles. Okay, and you will see that the motion looks very natural. Okay, so this is the work of students Mithun and Ravi, and this robot was actually built and demonstrated in CARE, but both are students, my students, and the research was done in ISC. Okay, so all the computation is done by a laptop, which the student is holding in its hand and walking. So you can see these cables. These cables are sending commands to the motors. Okay, and it is also sending power required for the motors. In an actual snake robot, the computing, the power source, everything will be on the robot itself. So one of the things is this algorithm or this robot is looking very natural. Okay, you can see that the links of the robot, the body of the robot will only bend when it is required, when it is near the obstacle. So as you can see, the head here is going straight and this part of the body is only bending. Okay, this part is still straight. So this gives a very natural looking motion to this robot. Okay, let's see it once more. Okay, so now the head is moving such that it is trying to avoid this obstacle and go through this path. The rest of the body is still straight. Okay, this is what I meant by a very natural looking motion. The next video is that of a 3 RPS parallel robot which was built in ISC by students for sun tracking. Okay, so in solar energy, one of the approaches is to provide a mirror or use a mirror which can reflect the incident sunbeam onto a receiver. Okay, so if you have lots of these mirrors and all of them are working properly and focusing the reflected beam onto a receiver, that place will become very hot. And then you can use an engine or some working fluid to run an engine such that you can eventually get electricity. Okay, so one of the important part of this solar energy harvesting is to track the sun. So we know how the sun moves across the sky throughout the year and on a particular day. So it moves roughly east-west, but it also moves a little bit north-south during the season. So there are various parallel robots and serial robots which have been used to track the sun and focus the reflected beam onto a receiver. So on the right I am showing you a 3 RPS robot. It's a parallel robot, okay, which have been built in ISC, which we have discussed earlier. And on the left is a serial robot which has two motors one after another. So there is a motor which is vertical, so it gives the vertical or motion about this vertical axis. Then there is another motor which gives the elevation. So this is called as the azimuth elevation configuration. So by rotating these two motors properly, I can make sure that the reflected beam from the sun as the sun moves across the sky is always on this receiver. Okay, so what I am going to show you is that there are these two robots which were built, two mechanisms. Okay, one is a 3 RPS robot and one is this azimuth elevation configuration. Both are controlled from a laptop, and you can see both of them are moving in a way such that the beam is focused onto that tower or to this water tank actually. Okay, so both configuration can track the sun and reflect the rays onto the structure. So at different times we have taken these pictures and then we have animated these pictures. So as you can see that the mirrors are moving. Okay, so there are of course some errors. Ideally, it should be exactly focused at the same place all the time. And of course, you saw that there was a cloudy period where there was no reflection. Okay, so as you can see now, it has rotated quite a bit. as we go towards the afternoon, late afternoon. So this robot was developed by students, PhD students at ISC. This is the roof of one of the buildings where interdisciplinary research on solar energy was being done. These are solar panels, and we also put up these two mirrors which for sun tracking. The last video which I'm going to show you is a flexible manipulator. Okay, so basically these are two videos, two side-by-side videos of an independently actuated endoscopic catheter. Okay, so we will see what is an endoscopic catheter also. I've discussed this earlier. So basically at the end of an endoscope, we will put this device and then we can independently actuate this device so that we can visit different points inside the stomach. Okay, at the end of this device where this LED is, you could have something else. You could have a grasper or you could have a scissor which you can articulate and you can take samples. Okay, so the interesting part of this product is that these are actuated by what are called as miniaturized pneumatic artificial muscles. Okay, these are very thin 1.2 mm diameter braided silicon tubes. The entire assembly is about 8 mm in diameter. And by pressurizing these tubes, okay, from an external source of air pressure, I can contract these silicon tubes. Now there are 3 of these silicon tubes on this actuator, endoscopic catheter, and by energizing them in a certain way. So for example, if I energize 2 and leave the other one thing, it'll contract in 2 directions and hence it will move in a resultant directions. So these 3 tubes, silicon tubes, are arranged 120 degrees apart, and by suitably pressurizing one or more than one at a time, I can make this end move on the surface of a hemisphere. Okay, and as I'm showing you, we can move about plus minus 2.5 centimeter, okay, from a central place, and this motion can be controlled by a joystick from outside. Okay, so the key feature is that these are very, very thin actuators. So everything is fitting inside 8 mm diameter, because in an endoscope, we don't have too much space. You know, when you are doing endoscopy, the clinician will put this through your mouth. Okay, and maximum diameter near your throat is of the order of 12 mm, 12 to 14 mm. Okay, so your device, which you are going to push into your stomach to take pictures or do some diagnosis, cannot be very wide. Okay, and we built this device, which was very, very thin diameter. So as you can see from the scale, it can move between plus 0 to about 25 mm, both sides. And the other view also shows some 0 to 25 mm. Okay, about little more than 25 mm. So it moves not very fast, but it does move, as you can see. Okay, so the last video which I'm going to show you is that of a cable-driven gripper. Okay, this is a continuing work. So basically, we want to make very flexible fingers, okay, which are driven by cables. Okay, so each finger consists of a 3D printed flexible backbone with discs. So in this finger that is shown, okay, so these are discs and there is a backbone. Okay, and when you pull these cables, these fingers will bend. Okay, so each finger is actuated by one or more cable. There are three fingers which are used for grasping and provide motion to the grasp object also. So as you can see, we pick up something or we grip something and then we can move it. Okay, so a large amount of mathematical modeling has been done to arrive at some reasonable mathematical models, and it is shown that the mathematical model and the simulation results match reasonably well with experiments. Okay, so this is also developed by students at the robotics lab in ISC. So all the three fingers are identical, but depending on what kind of motion you give to each finger, the object will move in some different ways. One more set of videos is from a collaborative work done with the Robert Bosch Center for Cyber Physical Systems. So we are working on this four-legged quadruped. Okay, so the basic idea is that these quadrupeds can go over uneven terrain. It can explore uneven terrain. So initially the work was started in the robotics lab, but now it is taken over and done in much more sophisticated manner in the Robert Bosch Center for Cyber Physical Systems. Okay, so I'm going to show you a video which will show what was the initial state and what was being done, then how the new robot quadruped called Stork was designed and fabricated, and then how some sophisticated learning algorithms are being ported on this robot so that it can learn to walk properly. Okay. So on the left, what you can see is this robot, which is four-legged, and it was walking using some algorithm, which is based on a central pattern generator. Next, this is showing the various stages of assembly of the more refined stock robot quadruped. All the parts are being assembled, and you can see that we have also done some simulation. Okay, and then we can show that it can turn, it can trot, it can bound, and it is also robust. The motion is quite robust because even if you push it to one side, it will come back on its track. So a large amount of learning and reinforcement learning is being done using some software tools. Okay. So what you can see is it has learned how to walk, it has learned how to bound, gallop, trot, various kinds of walking it has learned.
Regarding the different applications and the prototypes in the ISC Bangalore. Now we will start with the types and classification of robots. Okay, so a robot could be fixed or mobile. Okay, obviously mobile means it can be transportable or portable. It can be serial or parallel. I will show you examples, and also it can be classified according to the degrees of freedom. Okay, it can be rigid or flexible, and it also depends upon how it will be controlled. It could be a point to point control. Okay, it could be autonomous, it could be intelligent, and so on. So most of Most older instrument industrial robots, it has fixed base and consisting of links connected by actuated joints. Okay, so out of this fixed and mobile, most original industrial robots has fixed base. There are a few mobile robots which can now move in the factory floors, transporting the materials and tools from one place to another. It can even more or uneven terrain, and there are robots which can even walk and swim and slide. Okay, now we can see here this one. So how about a serial versus parallel comparison? Okay, so now the robot on the left is a very well known serial robot. Okay, this is a Puma robot, which is originally made by this company called as Unimation Incorporation. Okay, we have seen this in the earlier slides. So it has 6 degrees of freedom. So basically, there is a joint or a motor. Okay, here, and there is another motor. Okay, here, and there is another motor here. Okay, so it has 6 degrees of freedom. Okay, you can see here 3 rotation at the wrist. Okay, so this shoulder and this forearm can move all with respect to the waist. Okay, at the base and at the end. So at the end there are these 3 joints which interact to form a wrist. So it is very similar to your human arm, and that is why sometimes these were called as anthropomorphic. Okay, whether I am not able to pronounce this, but it is quite called anthropomorphic robots. Okay, so this is a serial robot because we have one link. Second link is after the first link. Okay, third link is after the second link, and so on. It is one after another. That is what why it is called a serial robot. You can also have parallel robots. Okay, and the most famous parallel robot is this steward of platform. Okay, or of steward platform. So it's basically in this robot there is a fixed base. Okay, you can see here this is a base is fixed, and there is a moving top platform, and in between this top platform and the fixed base there are legs, and these things are called as legs. Okay, a leg consists of a hook joint. Okay, a universal joint, a spherical joint, and a sliding joint. Okay, so this leg consists of a hook. Again I will repeat, it consists of a hook joint, then it also consists of a universal joint. Okay, this universal joint, a spherical joint, and a sliding joint. Okay, so by moving this sliding joint in and out, okay, so changing this length of the link, I can make the platform perform various kinds of motions. Okay, so we will look at this both Puma and Stewart platform later in the second chapter in case of kinematics of serial and parallel robots. Okay, so as I said, a serial robot has a fixed base, links and joint connected sequentially, and endings in an end effector. So at the end there is a end effector which you can fix a welding gun or a paint. Okay, or various other things. Okay, or you can even carry a screwdriver, go and tighten some screw. A parallel robot here on the other hand is not sequential, it is not after another. Okay, one after another, there are what are called as loops. Okay, so I can start from here, go to the top, come back again, and then one loop. So there are several such loops. So one loop is this, so one loop, this is the second loop, and so on. Okay, so the other feature of a parallel robot is that there is no natural end effector. Okay, natural end effector like this one. Okay, so in case of Stewart platform, it looks like the top platform is the end effector. Okay, and it is a natural end effector. But this top platform is a end effector. But there are many parallel robots where you can have more than one output link. Okay, you can choose your output link. Now a robot can also be classified according to the degrees of freedom. So this degree of freedom, okay, DOF, it is nothing but it determines the capability of a robot and the number of actuated joints. So if you have 6 degree of freedom, that is what is required to arbitrarily position and orient an object in 3D space. Okay. So in case of 3D space, you have X, Y, Z positions and also orientation. So to achieve this arbitrary position and orientation, we need 6 degrees of freedom. Okay. So for example, painting and welding can be done by 5 degrees of freedom because there is not much gain in rotating the welding torch, but its last axis. Electronic assembly can is used usually done by using 4 degrees of freedom. Okay, that is a SCARA robot. Okay, so I want to move in XYZ direction, go up and down, and also in XY. Also rotate this pin or chip so that it enters the PCB. Okay, so for extra flexibility and working volume of 6 degree of freedom, it can be mounted on a 2 or 3 degree of freedom. Okay, gantry on a wheeled mobile robot. So I can have a 6 degree of freedom robot. I can put it on a mobile robot and it can go various places. So the entire system now has much more than 6 degrees of freedom. You can also have redundant robot which with more than 6 degrees of freedom for avoiding the obstacles and also flexibility. Okay, so I will show you. Uh, we have already seen the video of a redundant robot which can be used to avoid the obstacles. Okay, so there are many more joints in that redundant robot or many more degrees of freedom than what is required. The arrangements of these first 3 joints in fixed serial robots are sometimes classified in 3 ways or 4 ways. One is called as Cartesian, then the second one is called as spherical, and on third or cylindrical. So basically, the motion can be described by Cartesian, spherical, or cylindrical coordinates. Okay, so first 3 joints would be x, y, and z, or it could be spherical r, theta, and phi, or cylindrical r, theta, z. We also have anthropomorphics like the puma. Okay, so we have one shoulder, we have one upper arm, we have one forearm. Okay, these words, okay, anthropomorphic, as I mentioned it, okay, as I mentioned it means human arm like. We can also have SCARA or selective compliance adaptive robot arms. SCARA stands for that, and this is the extensively used in electronic assembly. So SCARA means selective compliance adaptive robotic arm. The last 3 joints form a wrist. Okay, most of the time it is used for orienting the tool or the end effector. Okay, the first 3 joints typically are used to position the object in the 3D space, and the last 3 joints can be used to orient the object at the place where you want to be. Okay, now, so rigid versus flexible. So there is an example of rigid robot. Okay, this is again the another Puma, but not the 560, but another Puma which was developed by the same company, Unimation. Okay, so this is a 700 series industrial automation robot. Okay, this is very rigid and very heavy because We do not need any vibration. Okay, I want to, so suppose if I want to position this tip very accurately without any vibrations, whereas the space shuttle arm is very flexible. Why? The reason why, because in order to send a heavy robot, you have to spend a lot of energy. So weight comes with the plenty. So the weight will come with the penalty for space applications. So the links for this space shuttle arm are really flexible. Okay, you can see here are the length. The links are very flexible. Okay, so flexible that you cannot move them on earth easily. Okay, you have to go inside a swimming pool and make sure it is floating properly, and then move it and do all the testing. Okay, you cannot make it on a environment. Okay, normal room. You need a swimming pool for that. If you move it in a gravity, normal gravity in air, it will bend. Okay, so now this was the last part of the introduction and application of robots. Okay, there are different also control and mode of operation. Okay, for example, most older industrial robots we were seen that were teach and playback. Okay, so robot is taken manually through the task and positions are recorded. So during actual operation of the robot, so during actual operation of that robot, the robot plays back the thought sequence. Okay, very time consuming to teach, and robot cannot react to any changes in the environment. Then are computer controlled robots. So inputs are given from a computer after being tried out in an offline programming system. Okay, then sensor driven robots. Sensors are used to avoid obstacles and to take the decisions. And last one, the intelligent robot. Robot can learn about the environment using artificial intelligence and perform efficiently. This was regarding the first chapter and the first part of the chapter. So the next lecture we are going to start with the different transformation of a robot and position and orientation of a rigid body. Okay, so do watch this video and take care and have a peaceful life. Okay.